Right now, as you watch this, the Andromeda galaxy is hurtling toward us at 110 kilometers per second. That is fast enough to travel from the Earth to the Moon in about 1 hour, and it is dragging 1 trillion stars with it. For decades, astronomers treated what comes next as settled science. Our Milky Way and Andromeda would smash together in about 4 billion years, merging into one massive galaxy in the most violent event our corner of the universe will ever see. But in 2025, a team of researchers ran 100,000 simulations of this collision and discovered something nobody expected. There might only be a 50% chance it happens at all. So what changed? And if these two galaxies do collide, what happens to the Sun, to Earth, and to every star in both galaxies? To answer that, we need to go back over 100 years to a telescope in the Arizona desert, where one astronomer accidentally discovered that something enormous was heading straight for us. The year was 1912. An astronomer named Vesto Slipher was working at Lowell Observatory in Flagstaff, Arizona, pointing the 24-inch Clark refractor telescope at what everyone at the time called the Andromeda Nebula. Nobody knew what it was, just a fuzzy smudge in the constellation Andromeda that had puzzled astronomers for centuries. Slipher exposed a photographic plate for over 20 hours across multiple freezing desert nights. When he finally analyzed the light, the results stunned the entire astronomy community. Andromeda's light was blue shifted. That meant it was not moving away from us like almost everything else in the sky. It was coming toward us, and fast. Roughly 300 kilometers per second, making it the highest celestial velocity ever recorded at the time. But here is the thing, nobody even knew yet whether Andromeda was inside our galaxy or outside it. That question sparked what became known as the Great Debate of 1920, where two astronomers publicly fought over the size of the universe itself. The debate raged for 3 more years until a young astronomer named Edwin Hubble settled it forever. Using the massive 100-inch Hooker telescope at Mount Wilson Observatory in California, Hubble identified a Cepheid variable star inside Andromeda on the nights of October 5th and 6th, 1923. These pulsating stars act like cosmic distance markers because their brightness follows a predictable pattern discovered by astronomer Henrietta Swan Leavitt. Using that relationship, Hubble calculated the distance to Andromeda at roughly 900,000 light-years, far beyond any proposed edge of the Milky Way. He found 12 more Cepheids, confirming the result. When he wrote to Harlow Shapley with the news, Shapley reportedly looked at the letter and said, "Here is the letter that destroyed my universe." By January 1925, the matter was settled. Andromeda was its own galaxy, and the universe was unimaginably bigger than anyone had thought. So now astronomers had 2 critical facts. Andromeda was a separate galaxy, and it was heading toward us. The obvious question became, will it actually hit us? The first serious attempt to predict a collision came from physicists Franz Kahn and Lodewijk Volcher in 1959. They used what is called the timing argument. The idea is clever. Assume the Milky Way and Andromeda formed near each other after the Big Bang, flew apart with the expanding universe, then were gravitationally pulled back toward each other. Their calculations predicted a close approach in about 4 billion years, but there was a problem, a big one. They only knew how fast Andromeda was approaching along our line of sight. They had no idea whether it was also drifting sideways. If Andromeda had enough sideways velocity, it could sail right past the Milky Way like 2 ships passing in the night. Measuring that sideways motion at 2.5 million light-years away seemed practically impossible. The shift would be equivalent to watching a coin slide 20 centimeters on the surface of the Moon. It took 53 years and a $1 billion space telescope orbiting 350 miles above the Earth to crack the problem. On May 31st, 2012, NASA announced results that changed everything. A team led by Roland van der Marel at the Space Telescope Science Institute used the Hubble Space Telescope to observe deep fields in the Andromeda galaxy at 2 different times, separated by 5 to 7 years. By tracking how Andromeda's stars shifted against the fixed positions of distant background galaxies, they measured a sideways velocity of just 17 kilometers per second, with an uncertainty of plus or minus 17, statistically consistent with zero. That meant Andromeda's orbit was almost perfectly radial, a near head-on collision course. Companion simulations projected a first close approach in about 4 billion years and a complete merger in roughly 6 billion years. Headlines: Around the world declared our galaxy's fate sealed. And then the European Space Agency's Gaia spacecraft complicated things. In 2019, van der Merel and colleagues used Gaia's data to measure Andromeda's three-dimensional rotation for the first time using individual stellar proper motions. The revised sideways velocity came in significantly higher at about 57 kilometers per second. That changed the trajectory from a direct hit to more of a glancing blow, and pushed the first encounter back to roughly 4.5 billion years. Then came the bombshell. On June 2, 2025, Till Sawala from the University of Helsinki and collaborators including Carlos Frank from Durham University published a paper in Nature Astronomy that rocked the astronomy world. No certainty of a Milky Way and Andromeda collision. Using 100,000 Monte Carlo simulations incorporating 22 different variables and the latest Hubble and Gaia data, they found something that completely upended decades of consensus. The probability of collision within 10 billion years dropped to just 50%. The chance of the traditional head-on crash within 4 to 5 billion years was only about 2%. And if the merger does happen, it most likely occurs around 7 to 8 billion years from now, not 4 billion years. The secret saboteur turned out to be the Large Magellanic Cloud, a satellite galaxy of the Milky Way whose gravitational pull is slowly tugging our galaxy off course and away from Andromeda. In roughly half the simulations, the two galaxies fly past each other at about 500,000 light-years separation. Carlos Frank put it bluntly. Until now, we thought this was the fate that awaited our galaxy. Now we know there is a very good chance we may avoid it. Although Harvard astronomer Avi Loewy published a follow-up analysis in early 2026 that restored the merger probability to around 90%. The scientific community is genuinely split, and the next Gaia data release expected in summer 2026 could settle the debate. So what happens if the collision does occur? What does it actually look like when two galaxies containing over 1 trillion stars smash into each other? First, you need to understand what we are dealing with. The Milky Way stretches about 100,000 light-years across and contains somewhere between 200 and 400 billion stars. Its total mass, including the invisible dark matter halo, comes in at roughly 1.5 trillion times the mass of our Sun. Andromeda is even bigger. Its disk spans about 220,000 light-years, roughly twice our diameter, and it holds around 1 trillion stars. For decades, astronomers assumed Andromeda was far more massive overall, but a 2018 study recalculated Andromeda's total mass at only about 800 billion solar masses. The Milky Way might actually be the heavier galaxy, despite having fewer stars. The difference comes down to dark matter. Our galaxy appears to sit inside a more massive dark matter halo than Andromeda does, which is a plot twist nobody saw coming. The two galaxies are currently 2.5 million light-years apart. If the Milky Way were a dinner plate, Andromeda would be another plate about 5 meters away, only 20 plate diameters of separation. Galaxies are surprisingly close relative to their size, which is why collisions happen all the time across the universe. Here is the part that surprises everyone. Not a single star is likely to hit another star. The reason is that space between stars is absurdly empty. The average distance between neighboring stars is about 4 to 5 light-years, which is roughly 30 million times the diameter of our Sun. If the Sun were a ping pong ball sitting on a table, the nearest star would be a pea about 1,100 kilometers away. A galaxy collision is less like two cars crashing and more like two enormous swarms of fireflies passing through each other. The fireflies are so far apart relative to their size that virtually none touch. What collides is the interstellar gas. Vast clouds of hydrogen and cosmic dust slam together, compress through shock waves, and ignite massive bursts of new star formation. We can actually see this happening right now in real galaxy mergers across the universe. The antennae galaxies, a pair of colliding spirals about 45 million light-years away, captured in stunning detail by the Hubble Space Telescope, show star formation rates roughly 50 times higher than the Milky Way's current output. Hundreds of young star clusters, each containing over 1 million stars, are being born in the collision zone. During the Milky Way and Andromeda encounter, gravitational tidal forces would warp both galaxies well before they actually overlap. Thin streams of stars called tidal tails would be flung into intergalactic space, stretching over 300,000 light-years from the merging system. The galaxies would make a first close pass, swing apart, slow down, fall back together, pass through each other again, and finally coalesce over roughly 2 to 3 billion years. NASA and the Space Telescope Science Institute created a famous sequence of illustrations in 2012 showing what the night sky would look like from Earth across this process. Right now, Andromeda is the most distant object you can see with your naked eye. Its bright core appears about half the width of the full moon, but in long exposure photographs, its spiral arms span about 6 full moons side by side. And here is something wild. A 2020 Hubble study called Project Omega, led by Nicholas Lehner at the University of Notre Dame, found that Andromeda's gaseous halo extends 1.3 million light-years toward us, while ours extends about 1 million. At 2.5 million light-years apart, the halos are already overlapping. The collision has technically already started. By 3.75 billion years, Andromeda fills the sky and begins warping the Milky Way's band of starlight. During the first close approach, the sky erupts with new star formation. Emission nebulae, young blue star clusters, and clouds of glowing ionized gas paint the heavens in colors no human has ever seen. After the first pass through, both galaxies are stretched and warped with streams of stars arcing across the sky. By 7 billion years, the merger is complete. The familiar band of the Milky Way is gone forever, replaced by the glow of a massive elliptical galaxy. If you are still watching at this point, you clearly love this stuff. Hit subscribe, because we go deep on space and science topics like this every single week. Now let's talk about what all of this means for our planet. So what happens to us, to our sun, and our little rocky planet? The good news is, the solar system would survive. Stars are too far apart to collide, and gravitational tidal forces at typical interstellar distances are way too weak to strip planets from their orbits. A landmark simulation by researchers T.J. Cox and Abraham Loeb, published in 2008, tracked the sun's probable path through the merger. They found a 12% chance of being flung into a tidal tail during the first galactic pass, a 50% chance of ending up at 3 times our current distance from the galactic center, and a 2.7% chance of temporarily becoming bound to Andromeda before the final merger. Basically, we would get relocated, not destroyed. The cosmic punchline that makes all of this weirdly irrelevant for us is that Earth will already be dead long before any of this happens. The sun gets about 10% brighter every billion years. Within 1 to 1.5 billion years from now, that increasing luminosity will boil away Earth's oceans. All complex life will be gone by roughly 2.8 billion years. The most spectacular phase of the galactic collision, around 3.75 to 4 billion years from now, will play out over a scorched, lifeless Earth. As Tilsawala noted in 2025, the end of the sun is far worse for our planet than the collision with Andromeda. Now for arguably the most extreme physics in this entire story, the supermassive black hole merger. At the center of our Milky Way sits Sagittarius A star, a supermassive black hole with a mass of about 4.3 million suns, first imaged by the Event Horizon Telescope in May 2022. At the center of Andromeda lurks a far larger monster at roughly 100 to 140 million solar masses, about 25 to 35 times more massive than ours. After the galaxies merge, these two black holes would spiral toward each other through dynamical friction, flinging nearby stars outward at tremendous speeds. They would form a bound pair and face what physicists call the final parsec problem, where the stars needed to absorb their orbital energy have been ejected. But the 2023 detection of a gravitational wave background by the NanoGrav collaboration provides real evidence that nature solves this problem. A 2020 simulation published in Astronomy and Astrophysics by Schiavi and colleagues found that coalescence occurs in less than 17 million years after the galaxy merger completes. Just before the final plunge, the system would radiate gravitational waves with the power of 10 quintillion suns. And if enough gas is available, the merger could briefly power a quasar visible across the cosmos. The final merged galaxy has a name. Astronomers call it Milkomeda. It would be a giant elliptical galaxy, spheroidal in shape with no spiral arms, dominated by old red and orange stars slowly burning through their remaining fuel. Star formation would cease entirely after one last burst consumes whatever gas survived the collision. The Triangulum galaxy, a smaller spiral with about 40 billion stars, would likely get swept up too. Simulations give it an 83.5% chance of eventually joining Milkomeda. And in the very long term, something profound happens. Because the expansion of the universe is accelerating due to dark energy, every galaxy beyond our local group will eventually recede past the cosmic horizon. Within about 100 billion years, Milkomeda will be the entire observable universe for any future astronomer. A solitary island of fading stars surrounded by infinite darkness. Any civilization alive at that point would have no evidence that other galaxies ever existed, just their own stars and an endless void in every direction. We started this story with two galaxies rushing toward each other across 2.5 million light-years of darkness. For over a century, scientists have been piecing together what happens next, from Slipher's blue shift measurement at Lowell Observatory in 1912 to the 2025 Nature Astronomy study that turned a cosmic certainty into a coin flip. Whether this collision is our galaxy's destiny or just a close call, the Gaia spacecraft's next data release in 2026 might finally give us the answer. Until then, Andromeda keeps getting closer. 110 kilometers every single second, and nobody on Earth will ever live long enough to see what comes next. If this blew your mind, hit subscribe. We cover the biggest questions about our universe every week.